going to go through the notes for 1-5, solving equations and inequalities by graphing. This is going to be part 1 of the video. Part 2, we're going to look at using graphing technology to solve some of these problems. So we have our essential question: how can you solve an equation or inequality by graphing? Which brings us to example 1. We want to use a graph to solve this equation. So this is an equation that is very simple to solve algebraically, but we're going to demonstrate how to use a graph to solve this so that you can see how this may be beneficial for you. You want to take your left side of your equation and make that your y1. The right side of your equation, we're going to let equal our y2. I'm going to graph both of those equations, and wherever they meet, that is going to be my solution. Because I do need to go up to 20 for the y-intercept for y1, I'm actually going to count by 2's. However, I'm only going to label every 4 on my graph. And let's try that again. There we go. The same thing on the x-axis. I'm counting by 2's, but I'm going to label every 4. So my top equation, in blue, y equals negative 3x plus 20. My y-intercept is 20. And I need to go with my slope of negative 3, down 3 into the right 1. Since my x and y axis are counting by the same units, so each block represents 2 on each, I can actually count down 3 blocks and to the right 1 block instead of counting an actual down 3 and over 1. So this is really going to be down 6 and over 2, which is the same thing as down 3 and over 1. 1, 2, 3, 1, 1, 2, 3, 1. It's a good idea to make this go as far as you possibly can, especially because it's common with these types of questions to have to extend beyond in order to get a good picture. So now my second line, I have y2 is equal to 5. That is going to be a horizontal line at a height of 5. So I'm going to take my ruler and draw in my line of 5. So now I'm going to look and see where my lines meet. Well, it looks like they meet at that point right here, and it looks like the coordinates of that point are 5, 5. Now it does make sense that the y-coordinate here is 5 because one of the equations that I graphed was y equals 5. If we got a y that was not 5, then we most likely did something incorrectly because y equals 5 has to be a part of the solution. However, we don't use the y. Whenever we are stating what the solution to this equation is, I am only concerned about the x value. Because in the original problem, there was no y. We added the y's in order to graph, but y is not actually a part of our answer. To check that 5 actually is the solution for x, we would plug it in. So if I want to check that x is actually equal to 5, I want to go back to the original and check that negative 3 times 5 plus 20 is in fact equal to 5. Negative 3 times 5 is negative 15. And negative 15 plus 20 is in fact 5. So therefore, x equals 5 is my solution to this equation. Now again, this is one that was very easy to solve algebraically, but it did give you a demonstration of how powerful graphing can be to solve equations, especially when you come across equations that may not be familiar. When we start talking about the graphing technology tomorrow, you'll be able to solve anything as long as you can type it into a calculator. So here's part B. Again, I'm going to separate this into 2 different equations. My y1 is going to be the absolute value of x minus 4. My y2 is going to be 1/2 x plus 1. Now the top equation is an absolute value. So in order to graph this, I kind of want to keep in mind what my H and K are. And this goes back to section 1-2 whenever we were doing our transformations. So H comes from inside the absolute value. Remember, there's a minus in the formula. So my H is a positive 4. K is what's added outside of the absolute value. There's nothing there, so my K is 0. So negative 4, 0 is going to be the vertex of my absolute value equation. I want to pick a couple x's that are less than 4 and a couple of x's that are greater than 4 to plug in to get back the y's. You can make a table if you want to accumulate these. I'm just going to plot them as I calculate them. So if I plug in, say, 3 minus 4 is negative 1. The absolute value is positive 1. So 3 positive 1 would be another point there. If I plug in 2 minus 4 is negative 2. The absolute value is positive 2. So I have 2, positive 2. Let's go on the other side of 4. We look at 5. 5 minus 4 is 1. The absolute value is still 1. Look at 6. 6 minus 4 is 2. The absolute value is still 2. And then I can draw that, and you see I get a nice V shape there. I'm a little bit off on the left-hand side, but you get the idea. The red line is linear. So with this one, I can use mx plus b to plot. My b value, the y-intercept, is 1. So I'm going to plot that first. My slope is 1/2, so I'm going to go up 1 and over 2. Now please don't stop after 1 dot, because you can see I did intersect this absolute value in one place, but if this line keeps going, it looks like there is some other place out here on the right-hand side that I'm going to intersect. So I'm going to go up 1 and over an additional 2, up and over, still not there, and then up and over, it looks like I do finally intersect that graph. So we intersect in 2 places. This point is 2, 2. This point is 10, 6. Again, I don't need the y coordinates, but I do need to check the x coordinates to make sure those are actually solutions. So if I check x is equal to 2, I'm going to see that the absolute value of 2 minus 4 is equal to half of 2 plus 1. Well, 2 minus 4 is negative 2. The absolute value is positive 2. Half of 2 is 1, and 1 plus 1 is, in fact, 2. So that checks out. So x equals 2 is one of the solutions. Then we have to check 10. The absolute value of 10 minus 4, I want to see if that's equal to half of 10 plus 1. Well, 10 minus 4 is 6. Absolute value is still 6. Half of 10 is 5. And 5 plus 1 is 6. So 10 checks out as well. This has 2 solutions at 2 and 10. So those were 2 examples on solving equations by graphing. Now we're going to look at solving some inequalities. So this is example 2a. We want to use an inequality or a graph to solve this inequality. You are going to set up 2 equations like we did with example 1. My first equation is going to be the left-hand side, y equals x squared minus 4. My second equation is going to be the other side of 0. Well, 0, y equals 0, that is merely tracing the x-axis. So y equals 0, that is the same thing as the x-axis. And I want to know where the x squared minus 4 is greater than 0. So what you're really looking for is where is the blue line above the red line. Now for the blue line, that is a quadratic. So again, like we did with the absolute value, we want to identify the h and the k. And then again, you can make a table of values if you want to plot. The h value for this one is going to be 0. There are no parentheses. There is nothing inside with the x with the square on the outside, so your h is 0. Your k is going to then be your -4. So 0, -4 is where I'm starting. So we want to pick some x values on each side to get a nice picture of this parabola. If I go to the left first, if I plug in -1, -1 squared minus 4 is -3. If I plug in -2, -2 squared minus 4 is 0. Let's do one more just to finish it out on that side. -3 squared minus 4 is 5. So there's the left-hand side of my equation. The right side is actually going to mirror. If I plug in 1, 1 squared minus 4 is -3. You see that's the same as on the left. 2 squared minus 4 is 0. Again, that's the same as on the left. 3 squared minus 4 is 5. So that one is the same as well. All quadratics and absolute values are going to mirror. So now I want to know, where is the blue line above the red line? Well, all of these dots here, the blue is above the red, and all of these ones over here, the blue is above the red. So to state that as x regions, it would be all the x's that are less than -2, or you can use -infinity to -2 if you wanted to do interval notation. And you have all the x's that are greater than 2, or you can write it in interval notation as 2 to infinity. So it's really up to you which way you want to write it. If you want to write it with the set builder notation, or if you want to write it in interval notation, both of those would be acceptable for your answer. The last example we're going to do in this video has to do with a motorcycle and a car. And we want to know when will the car be ahead of the motorcycle? So we know a motorcycle is starting out 40 miles ahead of a car. The motorcycle travels at an average rate of 40 miles per hour, and the car is going to travel at 60 miles per hour. So my miles are going to be my distance on the y. For the x, this is going to be in hours. And I am going to extend this just a little bit more so that you guys can see that without getting interrupted. So we have the motorcycle and the car. The motorcycle is I'm going to write that in one in red. The motorcycle is starting out at 40. So at the beginning, the motorcycle is at 40. The car, change colors here, the car is at 0. The motorcycle is traveling at 40 miles per hour, and the car is traveling at 60 miles per hour. Popping this down so I don't have to keep scrolling back and referencing that. Now, rather than just looking at every hour, I actually went every half hour, and I'm going to plot a new dot of where my vehicles actually are. We want to know when the car will overtake the motorcycle. So at the beginning, the motorcycle is starting at 40. So if the motorcycle is traveling 40 miles every hour, in a half an hour, they're going to be traveling an additional 20 miles, which means the motorcycle is going to be at 60. So at 0.5 hours, so half of an hour, we're going to be up at 60. After a whole hour, we're going to be up at 80. An hour and a half, going to be at 100. At 2 hours, we're going to be at 120. And I'm going to go ahead and do 2.5 hours. That is going to put me at 140. So 2.5 hours, I'm going to be 10, 20, I think right about there. If you want to, you can connect those because you're looking at distance that the motorcycle is traveling. That is connected because even though you are at 40 and at 60 and at 80, somewhere you'll be at 70, somewhere you'll be at 75, so it is okay to connect those. Now we want to look at the movement of the car. After half an hour, well, first at the beginning, the car is starting at 0. After half an hour, the car is now up to 30 miles. That's half of the miles per hour. So 10, 20, 30 hasn't overtaken the motorcycle yet. At an hour, we're going to be at 60. Still hasn't overtaken the motorcycle, but it's getting closer. After another half an hour, we're going to be at 90. Again, getting very, very close, but the blue is still below the red. Now at 2 hours, because I'm going to be adding another 30 to this, I'm going to be at 120. And that's going to be your place where you overtake. And then we'll be way up at 150 at 2.5, which is up here. So when will the car be ahead of the motorcycle? After 2 hours. So any time that is greater than 2 hours, the car will then be ahead of the motorcycle. And you can see here, if you're looking at your table, at 2 hours, that is where they are exactly the same in position. And then when you move beyond the 2 hours, the blue column is going to be a higher number than the red column. So this is also an example of how you can use a table to solve and not just a graph. In the next video, we will be looking at using some graphing technology to solve some more complicated questions. So please review this, look back over the examples, rewatch it if you need to, and contact me if you have any questions.